students bring with them an amazing amount of talent and creativity and imagination and a lot of hard work to make these projects reality. So it's a great pleasure for me to introduce our first speaker, Mr. Carlos Cortez from the School of Mining Engineering, who comes from South America with a lot of experience in the mining industry in South America, who will be talking to us about water extraction from Mars. So join me in welcoming Carlos.
Okay, good afternoon, ladies and gentlemen. I'm sure I don't need to ask if you see me. I'm sure you can, or no. Well, today I will talk about a little bit of water extraction in Mars, or model. This is a joint effort between UNSW, different schools of mining, accounting, and space engineering, and also JPL. I would like to start with acknowledgement to JPL for allowing us to participate in this exciting project, a long-term trip. So yesterday, Professor Serkan Saydan and Dr. Bob Chisco introduced us a little bit about the Mars Colony Architect model. So I will not explain the model. This is not the aim of my presentation. Just to show you where we are, which is inside the mining model. At the end of the day, in simple words, our mission is to create or think about the technology and the most suitable system to become water extraction, liquid water extraction on Mars feasible. So we are in the WEM³ model. So we received several information and restriction from the model as well, and most important, physiological factors, which are significant restriction for all, and we fit the economic evaluation, which will be provide us the final analysis of feasibility. Well, I will not explain this slide again, but just like to stress how the Mars mission and becoming close to landing. So this is a good challenge for us, all of us. This is not a dream, it's reality. For those who are not familiarized with the mining industry, there is no mystery in the mining industry. This is an example of the typical open pit operation in huge scale for copper, iron ore, coal. In simple words, we have equipment for drilling, loading, and haulage, and the material it's processing. It's a cycle, it's a closed cycle where the material is loading from the face of the extraction point and carried to the downloading point, which could be dump deposit, waste deposit, or processing plant. It's a very simple. And the same concept, it's used for Mars. The only difference is that we use or we analyze several technologies. Has any kind of mining project, this is the main approach, we need to analyze any kind or any possible combination of systems, equipment, technology, production rate to reach the target. We use two main technology, the MISWI, developed by Dr. Zagnik, that we can hear today in the morning, and we adapt several technologies used for a massive drilling and excavation of rock, the tunnel boring machine and directional drilling, which is largely used in the oil and gas industry. And I had not enough time to include perhaps some technology that we saw yesterday for deep sea mining. Well, which is adaptation. The MISWI system has the capacity to do all: drilling, lift the material, processing, and carry water to the download point, which perhaps for us, for mining, is not the most efficient way to produce material. We are more familiarized with huge equipment, with massive mining and unitary operation. It means we have particular technology, equipment, and system to produce or to that are interested of one particular task. For instance, drilling machine, shovel, and trucks. We don't have drilling shovel trucks. This is something that perhaps for us, mining, in the mining point of view, is not quite efficient. And that's the reason that we adapt the MISWI system, which is the current or the most accurate information that we have to work on Mars, and have been tested for simulating or in simulating Mars condition. How this adaptation works is it's very simple. We just use the MISWI as a drilling machine just to extract from the ground, and all the other processes are separated. We have trucks or transporter and processing plant. At the end of the day, which is the adaptation, is just to remove the processing plant from the equipment. But also, we need to put it in a system, in an entire system. So as we decide to use this technology just as a drilling, we need to include some transporter and a processing plant. The same cycle that you said before in the mining, on Earth mining, no mystery here. So the adaptation of TBM is quite similar. The only difference is the design and the technology that we require, and the most important, the base of the mine method. This method, tunnel boring machine, it's a little bit more massive mine. It means can drill and excavate a huge amount, at least on Earth. This is the main difference. We have two ways to extract or to produce commodities, and I used the word commodity also for water. We can use quality and quantity. So this system provides us the capacity to work or to simulate high quantity production. So, and now, which is the WEM³, how this mining model works? We have a linear programming. Okay, this is simple. This is just an Excel file that we use to solve linear programming. I suppose I had 20 minutes, so I will skip some slides, and if you require more details, please let me know. I'm happy to explain you. And I have some assumptions based on the research on Earth and also from the test made in MISWI for Mr. Zagni. So the main restriction is how much water we need to produce. A simple configuration, we have a scheme in which kind of system are we working. We input the parameters, the technical parameters, the optimization target, some restriction, and finally we have the results, analyze them. A simple solve tool is used to reach this target. So which are the results? This is the first system, the adaptation of MISWI plus transporter. As you can see in the graph at your right, you can see that while the number of crew on Mars increased, the number of equipment increased dramatically. It means that perhaps this is not the most efficient equipment to be used for a high performance. In the other case, the TBM adaptation for Mars mining seems to be more efficient. So while I increase the number of crew, the number of equipment also increased, but in a smooth way. And this is the original configuration. How the MISWI works in an original design that do everything, drilling, processing, and haulage. You can see it's different, perhaps it's not quite efficient. Okay, but we have to put all this information all together. You can see in this graph the number of additional equipment that in each system that we need to feed more people. In other words, how many equipment I have to put in Mars, plus equipment, additional equipment, to feed 2, 3, or more crew. We can see the MISWI system require a large amount of equipment. And this is the economic analysis. This is interesting. We create an index, the equipment requirement index, that we just tell us how many equipment I require to produce a liter of water for different configuration. We can see that the MISWI is quite efficient for a low crew, for a small number of people. So this is quite interesting graph, because what's happened if we have the capacity to introduce the marginal cost, we perhaps could have a very accurate economic decision to choose not only the system, but also the technology, the number, not only the equipment, but how many people we can send to Mars and properly fit with water. We use this model not only for JPL, just for MCAM. Last week, there was in the last week of October, there was a forum in the US, and Kennedy Space Center asked us, can you take a look what's happened with the distance, which is the sensitivity of the distance for a particular area on Mars, the around curves. So, which is the trade-off? How far can I go? We adaptate the model, use some assumption from the original configuration of MISWI and information of around curves, where the region of interest fluctuates between 7 to 20 square kilometers. And we are talking about equipment of 2 meters. This is analyzed from the light to the dark color. The light are the lowest water concentration on Mars, 3%, 5%, and 7%. As you can see, while I increase the water concentration, I can go further. I can travel longer. Which is the problem? You can see at the top of the graph, the time required for the entire cycle, 24, 28 hours, means that I have to send a mission of 2 days to bring water. This is the interesting. At the bottom, we have the distance. At the bottom, we have perhaps the most flexible distance. In this area, we can use our equipment in a flexible way and also manage the risk to long missions, longer than 1 day. As I go further to look for water, to extract the water, if I have some kind of problem, I will take more time. So risk is also another consideration. At the top, perhaps it's a good idea also, but I will increase my launch weight and also my cost. And the third area, perhaps is not suitable due to the high risk of this long haulage activity. Just to summarize it, in conclusion, this is the first approach, and we discovered that perhaps the MISWI was quite efficient for low crew, for exploration or preparation for a massive mining extraction, and also adaptation of current technologies on Earth, tunnel-boring machine, directional drilling, or deep-sea mining must be explored in order to better understand which is the system that better perform. The landing site from the question of Kennedy Space Center, perhaps we have an answer, 5 to 6 equipment in a distance no longer than 2 kilometers. We narrow the area, and obviously we need more information, and this is the aim of this research that will continue. We need more information in terms of geology to assess the risk, develop a model from the most suitable technology for particular region of Mars. The equatorial region have different characteristics than the polar region, and the requirements for technology are different. So we need to explore the two regions and also introduce mechanical variables, which are quite important to manage our risk and efficiency, and also, as I said before, other technologies such as deep sea. I just like to finish this presentation with this image. This is the simulator of the moon mission in the 1970. The computer used in this simulator perhaps lower capacity than the current smartphone. So, and with this technology, they went to the moon. Thanks a lot for your time and your question. I appreciate it.
Questions?
Well, thank you for that. It was very interesting. The unit, your mining unit, the preferred one, the midweek, I think it was. How large is that unit in terms of dimensions and mass?
Okay, this equipment, it's approximately 2 by 2 meters. It's huge to send to Mars, but it's small because he drilled 10 centimeters. This perhaps is small for us, huge to send it, but it's small for mining purpose. That's the reason that we need quite accurate information in terms of geology. We need precision with this equipment. Yeah?
I was just looking at your kind of load and haul system, and normally you end up on a few sort of loading, feeding devices and lots of haulage trucks. You seem to have it the way around. Yeah, I would have thought in kind of low gravity, haulage would be really cheap, so you'd actually have lots more trucks, or the equivalent of trucks. I don't know what are you envisaging as a whole, like there's no pictures of how you hauling?
Well, if your question is related what kind of transporter we are using, basically it's an adaptation of the curiosity rover. We take the characteristics of this equipment and adapt to the loading, the payload, to just carry regularly. For sure, we need more information, we need more research, and this is the aim, as I told you, we need more information, and this is a very, very good point. We need to become Earth technology or current Mars technology more accurate for model.
Thank you.
My pleasure.
We're going to have to move on. Thank you, Carlos. Thank you, Carlos. Our next speaker.